Ever wondered how electricity is generated and transferred into our homes? It all starts with something we call direct current, or DC. This is a type of electrical charge that flows in a constant direction. It's like a river that never changes its course. This steady flow is crucial for many devices we use every day, from your smartphone to your car's battery. Understanding direct current is understanding the heartbeat of modern technology. It's time to delve into the fascinating world of DC generation. To understand DC generation, we first need to know its origin. The birth of direct current, or DC, stretches back to the late 19th century, a time of rapid scientific discovery and industrial revolution. The key figure in the development of DC was none other than the ingenious inventor Thomas Alva Edison. Edison, already known for his invention of the electric light bulb, understood that a stable and consistent source of electricity was needed to power his creations. This led him to develop the DC generator, a machine that could reliably convert mechanical energy into electrical energy. Edison's DC generators were the backbone of the first electric power systems, lighting up homes and factories alike. His dedication to improving and popularizing this technology laid the groundwork for the widespread use of electricity that we see today. So, the next time you flick a switch, remember Thomas Edison and the birth of direct current. Now that we know where it all began, let's explore how a DC generator works. A DC generator may look complex, but it's quite straightforward once broken down. Let's start with the armature. This is the heart of the generator, where the magic happens. It is essentially a coil of wire wound around an iron core. When this armature rotates in the magnetic field created by the field magnets, it generates an electrical current. Speaking of field magnets, they are the next key component. These are two powerful magnets placed on either side of the armature. Their job is to create the magnetic field in which the armature rotates. The stronger the magnets, the stronger the magnetic field, and hence the more electricity generated. Now, you might ask, how does this electricity get out of the generator? That's where the commutator comes in. It's a sort of switch that flips the direction of current every half turn of the armature. This ensures that the current always flows in one direction, hence the name direct current. But let's not forget about the brushes. They are small pieces of conductive material that maintain contact with the commutator, helping to transfer the electricity from the generator to the external circuit. And then there's the frame. It's like the skeleton of the generator, holding all the parts together and providing a pathway for the magnetic field. Lastly, we have the shaft. It connects the generator to whatever is driving it, like a wind turbine or an engine. As the shaft turns, it spins the armature, setting the whole process in motion. Each of these components plays a crucial role in the functioning of a DC generator. They work together in harmony, converting mechanical energy into electrical energy, and thus powering our world. With the parts identified, it's time to see them all come together. You've seen the parts, now witness the magic of DC generation. Let's dive into the step-by-step process of DC generation. The heart of this process lies in the conversion of mechanical energy into electrical energy within the generator. First off, we have the mechanical energy, often provided by a rotating machine, like a turbine. The turbine spins the generator's armature, a set of coils wound around an iron core. As the armature rotates within the generator's magnetic field, it experiences a change in the magnetic field around it. This change is crucial as it induces an electromotive force or voltage within the armature. This is known as electromagnetic induction, a principle discovered by Michael Faraday in the 19th century. Now here's where things get interesting. The induced voltage causes electrons within the armature to move, creating an electric current. But we're not done yet. This current is alternating, and we need it to be direct. Enter the commutator, a mechanical switch that flips the current's direction each half turn, converting the alternating current into direct current. And voila! We have direct current, a steady stream of electricity that flows in one direction, ready to power your devices. But remember, this process is continuous. As long as the armature keeps spinning, the generator keeps producing direct current, constantly converting mechanical energy into electrical energy. So that's how a DC generator works. Fascinating, isn't it? It's been quite a journey exploring the world of DC generation. We've delved into the power of direct current, unearthed its birth, and dissected the anatomy of a DC generator. We've navigated the intricate process of DC generation, highlighting the essential role these generators play in powering our daily lives. From the smallest gadget to the largest industrial machines, DC generators are the silent workhorses. And that's DC generation for you. Simple, yet profound. Until next time, keep learning and stay curious.